3 teachers with different backgrounds have come to CLEAPS, the school science support service, to find out about teaching radioactivity.
I haven't taught radioactivity before. I'd be quite nervous in teaching radioactivity because of the dangers of it and because of my lack of experience and knowledge in teaching it.
I've been a physics teacher for, well, this will be my 5th year. I've taught radioactivity at GCSE in all those years, as well as teaching it at A-level.
I'm currently a PGCE student and I've just started my 2nd placement, and so I've got no experience of teaching radioactivity yet.
If I reduce the voltage down from that though, I want the point where it's just stopped sparking. When I introduce the radioactive source, which is producing alpha particles, when one of those alpha particles fires through the gap between the mesh and the wire, it causes a spark. That's because each alpha particle, as it passes through, is causing ionisation, allowing a spark to happen between the grill and the wire. We can see the mesh across the top, which is connected to the negative side of the power supply, and the wire underneath, which is connected to the high voltage positive side. As the ionising radiation comes in, it causes the sparks to happen. As we zoom in, an alpha particle is coming from above, and it ionises one of the air particles between the gap. That's then accelerated upwards, and that causes a cascade of ions hitting each other, which we see as a spark. Each ionisation particle coming in is going to cause a spark of its own.
The spark counter can also be used to look at the absorption properties of alpha radiation using an americium source.
I'm going to hold the source so the alphas are being detected. When I put the paper in the way, it stops. To show that paper stops the alpha particles from getting through. I can now point out the range of the alpha particles, which is a few centimetres in air.
A more controlled way of handling the radioactive source is to mount it in a dowel rod and clamp it in a retort stand.
I think the idea of using dowels as holders and clamp stands is excellent. It actually allows you a lot more flexibility. And I'm going to go back and get my technicians to prepare me a set of dowels, because I think that's what I want to do from now on.
In this experiment, we'll be using a Geiger-Müller tube to measure beta and gamma radiation.
The tube has got a protective cover on the front, which if I carefully remove, you can see a very thin window which allows the radiation to pass in. This one here has had the end of the tube removed, revealing a central wire which is positively charged and a cylinder which is the negative connection. Every time the radiation comes in, it'll trigger an event which can then be counted by a machine.
Schools may have different types of meters, but essentially they all provide the same function: to provide the voltage to the Geiger-Müller tube and count the events.
Whenever you're setting up a radioactive source, you always make sure it isn't pointing at people. And a good setup is to use a retort stand with the radioactive source pointing downwards all the time and the Geiger-Müller tube at the bottom. Whenever you're using a Geiger-Müller tube, particularly if you're holding it in a clamp, it's very important to make sure you don't squeeze it too hard, because that too could damage the window.
For this experiment, use a pure beta source such as strontium-90.
I can get an audible representation of how much radiation I'm measuring. The first thing to do is to show that, unlike the alpha particles which are stopped by paper, the beta particles aren't. So putting a piece of paper in makes no difference at all. However, if I bring a piece of aluminium in, we can hear that the beta particles are completely stopped, because the range of beta particles is a few millimetres of aluminium.
What happens to the beta radiation?
As the beta particle enters the aluminium, it'll slow down, losing energy. In the end, it's likely to become part of the sea of electrons. The other thing we can demonstrate is the range of the beta particles in air, and if I move the source away from the detector, you'll hear that the count rate decreases. And notice that the range in air is significantly larger than the alpha particles, which was 2 or 3 centimetres. We're at tens of centimetres and still getting a reading on the counter. This time I'm going to use cobalt 60 as my gamma source. So I'm going to mount the gamma source above the Geiger-Müller tube.
That's quite a lot lower count rate.
There's two answers to that. The first is that the Geiger-Müller tube is not as good at detecting gamma rays. And secondly, the number of gamma rays produced by this source is quite low. If I put the aluminium in the way, the aluminium is not absorbing many of the gamma rays as they pass through. However, if I introduce some lead, it's only with a couple of centimetres of lead in the way that the count rate is significantly reduced, because gamma rays can pass through lead, but several centimetres starts to significantly reduce the number getting through.
Reduced but not stopped.
Yeah, to completely stop the count rate, we have to have several tens of centimetres of lead.
Why is it that lead stops it as opposed to another metal like aluminium?
OK, the aluminium itself is quite a light metal. Its density isn't very high, as opposed to lead, which is very dense, which will absorb the gamma rays as they pass through.
Handling the absorbers with the bare hands is quite safe. The problem arises if you're tempted to put the absorber close to the source with your fingers. So we always recommend that an absorber should be handled with forceps if you've got a radioactive source nearby.
What you see here are the 3 types of radiation streaming towards you. On the right-hand side here are the gamma photons. In the middle is the helium nucleus, the alpha particle, 2 protons, 2 neutrons. And on the left-hand side is the beta particle, the very fast electron. You'll notice that the gamma rays and the beta particles are almost travelling at the same speed. That's because the beta particle is travelling at a speed quite close to the speed of light. If I bring a piece of paper in, what you'll notice is the alpha particles are now unable to penetrate through. The gamma rays and the beta particles, though, can still get through. If I bring a piece of aluminium in, that's enough to absorb the beta particles, and they are no longer getting through, and there's no significant reduction in the number of gamma rays. If I bring in a large piece of lead, that is enough to absorb a significant number of the gamma rays, and the count rate drops right down.
Using the absorption demonstrations is a really useful way to check students' understanding of the penetrating properties of radiation.
The other thing that we can start to try and show with this setup is how the range of the gamma rays in air is linked to the inverse square law. So hopefully if I double the distance they are away, the count rate will go down by a factor of 4. So at the moment my source is roughly 4 centimetres away, and if I double that to 8 centimetres, the source will now be counting at about a quarter the count rate.
After having watched the alpha, beta and gamma absorption practicals, I think that I would be able to perform that in the classroom, along with the animation, which would help the kids' understanding.
This experiment shows that beta particles are negatively charged.
I've got them at an angle to each other so that the detector is not collecting the radiation as it's fired from the source. The aluminium plate is to block any stray beta particles from going straight into the Geiger-Müller tube. I can then use a magnetic field to deflect those beta particles around the shield into the detector. So as I bring the magnetic field in, the count rate increases significantly as they're deflected into the detector. And just to confirm that it's not the metal plate, if I reverse the field and bring it back in, I can see the count rate doesn't change because they're not being deflected towards the counter. I can confirm this with Fleming's left-hand rule, with my first finger representing the field, my second finger pointing in the opposite direction to the beta particles, and my thumb showing the direction that they will be deflected into the detector.
Once the students have seen some of the properties of alpha, beta and gamma radiation, you can start to discuss what they are. This is a good starter activity that will allow you to visualise it.
What you've got there is the hat is going to represent the centre of the atom, the nucleus, and the balls attached to the outside are going to represent the electrons around the outside. And what I'm going to do is I'm going to sort of simulate the idea of the ionising radiation as being fired towards you. Now I'm going to start with the light polystyrene ball. I'm going to try and knock off the electron hit. Or I could try the golf ball, and I'm not going to do that yet. But
You could ask students to discuss how these model the different types of ionising radiation.
a pulse of smoke.
I thought they were really good starters. They would be really great for rousing enthusiasm.
Using the protactinium generator, we can measure the half-life of a radioactive isotope. Once it is shaken, the decay can be measured using a Geiger-Müller tube.
What I need to do is to record the count rate every 10 seconds over 5 or 6 minutes. Reset the timer, and I'm going to write down the count rate every 10 seconds. And 10 seconds, 154. I've reset the counter. And what will happen is, over the 5 or 6 minutes, that count rate for 10 seconds will decrease as the half-life of the radioactive isotope continues on its decay curve.
Another way to measure the decay rate is with a computer data logger, which will plot the results on a graph. The count rate will increase for the first few seconds, so we exclude those. You can highlight that the points don't make a smooth curve because of the random nature of decay. But drawing a smooth curve through the points shows the trend of the readings. To help demonstrate decay and its random nature, you could get your students to play games like these. Flicking coins randomly eliminates players and is fairly quick.
If you're ahead, you stay in the game.
I'm out.
So Julie and I...
Tails.
I'm tails too, so we both lose.
And you can demonstrate isotopes with a longer half-life with dice, which have a lower probability of decay.
If you get a 6, then you're out of the game. You've got a 6, so Julie is out.
Another way is to use cubes with one side painted white. Mix them up and pick out all the cubes with the white upwards. Repeating this a number of times, the students can count each result and plot a decay curve.
It's really good in demonstrating the random nature of radioactive decay, isn't it?
Yes.
I've learnt there's an awful lot you can actually do. There's a big range of experiments you can do.
With a bit of practice now, I feel confident enough that I will be able to perform the practicals and demonstrations safely.
Actually, I'm teaching radioactivity next week, so I'm really looking forward to doing so.